Ever since we've been pointing spacecraft at the sun, 2 regions on our star have been missing from satellite images. The sun's 2 poles have never been mapped because all the solar images we've built have remained in the ecliptic plane, the swath of space roughly aligned with the sun's equator, where all the planets orbit. A new mission from the European Space Agency and NASA called Solar Orbiter aims to escape this plane and take the very first images of the poles.
The planets are all moving and circling the sun, and so we already have some velocity going one way. If we want to launch up out of the ecliptic, it requires more energy.
To get outside the ecliptic plane, Solar Orbiter uses and Venus's gravity to slingshot itself into a view of the poles. The only other satellite to fly over the poles was Ulysses, which launched in 1990 to study the solar atmosphere. But Solar Orbiter will be the first mission to capture actual images of this hard-to-reach region. Scientists think the poles could be the missing piece to understanding what drives the sun's activity. Every 11 years, the sun's magnetic field flips. North becomes south and vice versa. This mysterious process has direct effects on Earth. Before the poles flip, solar activity reaches its peak. The number of eruptions increases, sending powerful bursts of solar material that can potentially harm our astronauts and satellites.
We don't really have a good understanding of the global solar behavior.
Another one of the mission's goals is to monitor how these eruptions and solar material travel through space. Using a suite of 10 instruments, Solar Orbiter observes an active region on the surface as it explodes, and then also takes measurements as the escaping material passes directly by the spacecraft.
Solar Orbiter will give us a comprehensive, full view of the entire sun and how the sun is impacting throughout the entire solar system.
At closest approach, Solar Orbiter will be closer to the sun than Mercury, at a mere distance of 26 million miles away, the ideal distance to get a comprehensive view of the sun and its surrounding atmosphere. It will fly close to the sun every 6 months and endure temperatures more than 900 degrees Fahrenheit. To survive the intense radiation, a large titanium shield protects the instruments, while a carefully orchestrated dance of opening and closing eye holes in the shield allows the instruments to peep out at the right time. Other instruments will directly measure solar material from behind the shadow of the shield. All of these observations will tell us more about the sun than we've ever known before. And by the end of the 7-year mission, we will have seen our star in a completely new way.
Our understanding of the sun will change dramatically. I will say that we are living in a revolutionary moment in our field.
Hi, I'm Tori Bruno. I'm at the historic Space Launch Complex 41, home of the amazing Atlas rocket and soon to be home of the Vulcan Centaur rocket as well. And this is a very special day because right now we have an Atlas on the pad carrying the Solar Orbiter probe that will return to the Sun for even more exciting science. I am standing at a very unique vantage point. I am on top of the main liquid oxygen storage tank. This holds 465,000 gallons or 2 million liters of ice-cold liquid oxygen. It is chilled to minus 180 degrees C or nearly minus 300 degrees Fahrenheit. So a pretty special place to be standing with a great view of the rocket. Now, Solar Orbiter is a really interesting mission. We're going to launch it here on this Atlas with a very precise trajectory in an exact amount of energy, something we call C3, the characteristic energy, in this case 30.05, to send it on a perfect trajectory away from the Earth, escaping Earth's gravity well, and then doing gravity assists for several years with Venus and the Earth gradually pulling its closest point, its perihelion, inside Mercury's orbit to get a great view of the Sun, while lifting its inclination so that it will actually see, really for the first time ever, a direct view of the solar poles. So really exciting science, and a great complement to the Parker Solar Probe that we launched in 2018 on a ULA Delta IV Heavy rocket. Now, I get a lot of questions about the unique configuration of this Atlas. This is the one we call the slider, the 411. It has a single SRB, and the combination of that liquid core with that single SRB together give exactly the right amount of thrust. 5.3 million newtons or 1.2 million pounds of thrust to put Solar Orbiter on that exact trajectory. Now, the thing that I think always throws people is, gosh, the rocket looks so asymmetric. There's the center core with its liquid rocket engines, and then there's this big solid hanging off the side. How do you control and steer it? Well, two things. First, we have a fixed nozzle on that solid rocket motor that is canted at an angle so that its thrust vector passes through the average center of gravity of the rocket. So it has very little moment, much less than you would think if it were just, say, for example, pointing straight down. And then in addition to that, the RD-180 engines underneath the Atlas have a tremendous amount of thrust vectoring, what we call control authority, that can steer through any asymmetries that are left over as the center of gravity moves on that rocket. Even though the nozzle is fixed, it moves because the rocket is 90%, greater than 90% propellant. It is getting lighter and lighter when it flies, and the center of gravity is actually moving. So we can steer through all of that and provide this very precise trajectory. Well, I hope that was interesting to everybody. And now I've got to get back to work because I'm up here to do my job.
And liftoff of the United Launch Alliance Atlas V rocket.
The Atlas V RD-180 main engine and one solid rocket booster ignite to generate more than 5.3 million newtons of thrust to lift the rocket on its way towards a hyperbolic escape trajectory. Shortly after liftoff, Atlas begins a pitchover to attain the proper flight path while minimizing the dynamic pressure the vehicle experiences during flight. The Atlas V reaches Mach 1, the speed of sound, at 58 seconds. The single SRB is jettisoned at 2 minutes 20 seconds. At 4 minutes 3 seconds, the propellant levels deplete and the booster engine shuts down. 6 seconds later, the Atlas Centaur separation system activates to release the booster stage. The vehicle now weighs less than 14% of what it did at liftoff. 10 seconds later, the first burn of the Centaur main engine begins. This burn guides the Centaur into a near-circular parking orbit. Approaching payload, the Centaur is burning propellant at a rate of 23 kilograms per second, traveling at more than 17,700 kilometers per hour, and located nearly 134 kilometers in altitude and 470 kilometers downrange. At 4 minutes 27 seconds, the payload fairing is jettisoned. The vehicle now weighs less than 7% of what it did at liftoff, 4.5 minutes earlier. 12 minutes 14 seconds into flight, cutoff of the Centaur main engine, or MECO 1, occurs. The mission now enters a coast phase in preparation for the second burn. Because this targeted Earth escape trajectory varies from day to day, the coast and the second burn will vary to accommodate this. The Centaur main engine is restarted at 42 minutes 58 seconds for the second and final engine burn. Nearly 7 minutes later, final cutoff of the Centaur main engine occurs. At 52 minutes 40 seconds, Centaur releases Solar Orbiter for the European Space Agency and NASA to begin its nearly 2-year journey to the Sun. After using gravity assist maneuvers at Earth and Venus, Solar Orbiter will help us understand how our star creates and controls the heliosphere, a giant bubble of charged particles blown by the solar wind that permeates the whole solar system and influences the planets within it.